We've been asked to determine whether this series converges or diverges. And again, this was a set of problems we were working on in class where we assigned tests to problems and we were only allowed to use each test once. And this one ended up being the one we chose to use the alternating series test for. And this is going to be a challenge for us because actually if this problem showed up in the wild, I would probably actually do a different test, and I'm going to show you that at the end of the video. But for now, I'm going to make myself use the alternating series test, which makes me check 3 parts first. The first part of the alternating series test makes me check is that the u sub n's are all positive terms. Well, what are the u sub n's? Well, they're the part of the nth term formula where I chop off that minus 1 to the n plus 1. So for us, the u sub n's are these. N factorial squared all over 2 times n factorial. Well, those are all positive. Factorials are positive. When I square things, I get positive numbers. When I divide two positive things, I get a positive number. Now, what this is actually checking is to make sure this series actually alternates. That the only thing that is either a plus or a minus is that minus 1 to a power, making it always a positive times a positive or a negative times a positive, making sure that the terms always actually alternate in sign. Well, that was an easy part, so check. Next, we're going to need to make sure that eventually, for some value of n, the series becomes non-increasing. That the n plus first term is smaller than the nth term. That if I was plotting these u sub n's, eventually they go down. Or at least don't go up and then go down. That they are non-increasing. This is actually going to be a challenging part of this problem, so we're going to do that in just a moment. Another challenging part of this problem is to actually make sure that the u sub n's themselves go to 0 to evaluate this limit. Well, I'm going to justify this limit in a way that I don't think is too bad, but admittedly is a little hand-wavy. And this makes me realize that maybe if I met this problem in the wild, I wouldn't choose to do it in this way. And so what I'm going to do is I'm going to simplify this nth term formula. I'm going to say that n factorial squared is n factorial times n factorial. 2 to the n factorial, well, that would be 2 to the n times 2 to the n minus 1 times 2 to the n minus 2 times 2 to the n minus 3, and I just keep counting down, and eventually I will get to the number n plus 1 times n minus 1 times n factorial. Right, because that would eventually end in an n times n minus 1 times n minus 2, and I'd have that n factorial, so I could actually cancel off one of those, making this limit a little easier to deal with. N factorial over 2 times n times 2 times n minus 1 all the way down to n plus 1. And I've made a really bad decision trying to write that there, so I think I'll just rewrite that last statement. N factorial over 2 times n times 2 times n minus 1 times 2 times n minus 2 all the way until I get to an n plus 1. Now, that bottom started off as a 2 times n factorial, so that would have originally gone 2 times n times 2 times n minus 1, all these things, and then also included a times n minus 1, all the way down times 2 times 1. Well, if I think about it, if I just take an example and think about like n equals 6, then that bottom would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This is the bit that canceled off the n factorial. Well, easy to see, I'm counting from 1 to 12, there were 12 things. By canceling off the n factorial, I got rid of half of them. So there are, well, n things left, 6 things left. So on top, I have an n factorial. On the bottom, I have a 2 times n going all the way down. But there are n numbers here. There are n terms on the bottom. Well, that n factorial on top, if I write it all out, also has n terms. So if I write them both out in that way, I see this. All right, well from here, I'm going to look at a bunch of fractions to justify this particular limit going to 0. But at this point, I can also kind of imagine that on the bottom, I'm expressing everything as a function on n, but on the top, I'm not. Now that's a bit misleading, right? Because I could really think about that 2 there as being an n times an n minus 2. That is a function on n, but the n's cancel. Kind of thinking the degree of the bottom is higher than the degree of the top. The number on the bottom is certainly larger than the number on top. But I'm going to look at this written down just a little differently to justify this limit. Looking at each fraction over its corresponding part on top. So each number on the bottom over it, under its corresponding number on top. And when I do that, if I take a limit as n approaches infinity, well, this one's going to 1/2, this one's going to 1/2, this one's going to 1/2, and at the end, they're going to 0. And so if I'm thinking about that, I'm either getting a 1/2 or a 0, but I'm getting at least 1 0. So 0 times a whole bunch of 1/2s, and however many zeros I want, gives me that this limit is going to 0. So the u sub n's do go to 0. Leaving me only to check this bit of arithmetic, that the u sub n's are at least eventually decreasing. And so that is going to make me set up an inequality. I'm going to have to look at the n plus first term and compare it to the nth term. So let's get that set up. So the nth term, n factorial squared over 2 times n factorial, greater than or equal to the n plus first term. So that would be n plus 1 factorial squared all over 2 times n plus 1. So 2 times n plus 2 factorial. I want to find an n that makes this statement true, right? If I can find that value of n, I will have shown that this u sub n, this nth term formula for u sub n, is eventually non-increasing. Well, one of the nice things about this particular inequality is everything involved is positive. So I can multiply both sides by parts of it. I can divide both sides by parts of it without having to worry about flipping my inequality symbol. So I'm going to rewrite this thinking about dividing both sides by n plus 1 factorial squared. And multiplying both sides by 2 times n factorial. Getting, I don't know, the similar looking parts together. I'd say I'm getting the factorials together, but everything's got a factorial in it, so it's not really what I'm doing. So on this side now I have n factorial over n plus 1 factorial all squared. And on this side I have 2 to the n factorial over 2 to the n plus 2 times 2 to the n plus 1 times 2 to the n factorial. Right, just thinking about what factorials do, that if I'm looking at 6 factorial, I can think about that as 6 times 5 times, well, 4 factorial. I split off the first 2 parts, and that's going to let me do some very nice canceling. If we investigate the inside of this parenthesis, we actually find out that would become 1 over n plus 1. So by rearranging this statement with a bunch of factorials in it, I end up with a statement with, well, no factorials in it. I have a 1 over n plus 1 is greater than or equal to a 1 over 2n plus 2 times 2n plus 1. Now I want to solve this inequality. So to make it a little easier, I'm going to take the reciprocal of both sides. So I have n plus 1, and on this side 2n plus 2 times 2n plus 1. When I take the reciprocal of both sides, that greater than or equal to becomes a less than or equal to. I can solve this inequality for n. So I have n plus 1 is less than or equal to 4n squared. I have a 4n plus a 2n, so plus 6n plus 2. Getting everything on one side will give me a 4n squared plus 5n plus 1. So I have an inequality to solve, a polynomial inequality to solve. I'm going to go through and try factoring it. And I think this works. So 4n squared, 4n and 1n make 5n. This works. This side is equal to 0 clearly at -1 and -1/4. And so now I can go through and pick some test points to see what values of n make this side greater than or equal to 0. Positive. Well, this is really the only place I care about because all the n's I care about are positive. So I'm going to plug in a 0, which is on this side, and I get out a positive, so that's good. That's really all I need. This tells me for any n greater than or equal to -1/4, but I'm just going to say greater than or equal to 1. This statement is true, and because all of the things we did are reversible, it means this statement is true. So not just for some n, for all n greater than or equal to 1, my use of n's are eventually not increasing. And I don't even have to say eventually there. That was actually kind of dumb. Well, we check that, we check that, we check that. By the alternating series test, this series has to converge. So that was hard. This is a hard limit, and I only kind of verified it in a hand-wavy way. This part was challenging, and we really did verify it. So what would I do if I met this problem in the wild, right? If I wasn't constrained to using the alternating series test? Well, with all those factorials in it, I think I know exactly what I would do. I think I would use the ratio test, which is a test for absolute convergence. Well, fortunately, if I'm using the ratio test and I'm testing for absolute convergence, well, if a series converges absolutely, the series itself has to converge. So I'm going to be taking a limit as n approaches infinity of the n plus first term in absolute value over the nth term in absolute value. Well, by putting this thing in absolute value, it just gets rid of the -1 to a power. So I have the limit as n approaches infinity of, well, n plus 1 factorial squared all over 2n plus 2, right? Because the n plus 1 would go in there and I'd have to distribute it, factorial, divided by, well, the nth term. So I don't have to do anything now, just n factorial all squared all over 2 times n factorial. All right, let's rewrite this limit. And some of the arithmetic happening here in the ratio test seems familiar. Let's see if that's still on camera. It is. So I can leave the top alone just for a second. N plus 1 factorial squared all over 2n plus 2 factorial times 2n factorial all over n factorial squared. All right, I'm going to flip-flop things on the bottom to make the arithmetic easier to deal with. So everything I'm going to write here is being squared. So that's going to be an n plus 1 factorial over n factorial. Well, at this point, we know that's just going to be an n plus 1 times 2n factorial over 2n plus 2 factorial. At this point, we know that's 2n plus 2 times 2n plus 1. Putting all of that together, we're taking the limit as n approaches infinity of n plus 1 squared over 2n plus 2 times 2n plus 1. This is a rational function where the degree of the top is the same as the degree of the bottom. On top, I have a 1n squared. On the bottom, if I multiply this out, I'd have a 4n squared. That's going to 1/4. In the ratio test, that's a value of what we call rho. And when rho is less than 1, our series has to converge absolutely. So by the ratio test, this series converges absolutely. So, as an alternating series test example, this is very hard. As a ratio test example, just one limit that is actually fairly straightforward. So we were constrained by the instructions from class. Without that constraint, this problem would be easier. Always remembering that when we're choosing a test, it's nice to think about which one's going to be the easiest.